What's going on, everybody? This is Mr. Diamond having a really frustrating morning. This is about 20 plus minutes of me trying to figure out how to do this before I realized that I didn't even need to do the thing I was trying to do. So I apologize for that. Also, I think I forgot to turn down my mic audio, so if I'm really loud, I'm sorry. I'm really loud. We're going to be talking about advanced molecular geometries today. I'm going to work out an example problem on this here note slide area right here. I'm not going to need to actually do anything super crazy for it. It's really just going to be explaining. But then after that, we're going to stop halfway through, and I'll get into hybridization as the second section of this. And that one I will probably be recording at my house so I can transition to being able to write on a piece of paper in front of me. I'm having issues getting that to work here with the number of USB ports and the dual monitors and stuff like that. But anyway, that's none of your problems. That's all my problems. So this sheet, or at least this top portion of the sheet, should look familiar to at least all of you guys who took my class. We used this top portion of the sheet when we were talking about our geometries. Now, I am here acknowledging to you by showing you the rest of this that I was also, misleading you a little bit. There was actually a little bit more on the graph or on the chart that could have been used. For example, if you can actually have a steric number of 5 or 6, and all the stuff we worked with only had a steric number of up to 4. Having higher amounts of possible things you could have, up to 5 or 6, means that there could be 3 or 4 lone pairs instead of just 1 or 2. So our geometries are a little bit more complex here. For the most part, what we're going to be dealing with, though, are linear, trigonal, planar, bent, tetrahedral, trigonal, pyramidal, or bent. And we called this one rare bent and this one normal bent. That's how we distinguish between them. Now, there's also trigonal bipyramidal, sawhorse, T-shape, linear, but this one has 3 different electron pairs. And then if my thing gets out of the way, octahedral, square pyramidal, I believe that's square planar. Yeah, square planar, T-shape, and then linear with 4 pairs of electrons. So all of these are possible geometries. We're still going to stick mostly with this top one, and there might be one on the test like this, or it could be in the bonus, but I will possibly ask you about one of these not as a bonus question. Don't feel like you have to have them memorized, though. That would just be like 1 point. And the basic way to solve this is you look at this steric number, which is how many things is it attached to. That includes lone pairs, and that includes any other groups. It could be single bond, double bond, or triple bond. If it's attached to exactly 2 things with 0 lone pairs, it is linear. And if it's attached to 2 things and one of those things is a lone pair, well, the only way you can have it attached to 2 actual things that aren't electrons is if it's just a straight line. So anytime you get to something where it's like one thing bonded to one other thing, it doesn't matter how many electrons that there is on this piece, it's still going to be a linear geometry. It's the only thing you can do with 2 things. Connect them with a straight line, or with 2 points. You can connect them with a straight line. I apologize. It's really early when I'm recording this, as you can tell by me still having tea. Now, for the more complex ones, for this one here, this is a representation of water, or water is an example of this. Water has hydrogen and hydrogen. Hydrogens have linear geometries because they're only attached to one thing, but the oxygen has 2 sets of lone pairs and the 2 hydrogens it's attached to. That's 4 total things it's attached to. 2 of those things are lone pairs. That's how you know that it has a bent geometry. The rest of the chart just works that exact same way. And if I get reminded to, or if I remember to, there should be a post or a link to this on Google Classroom as well, so you can go and look at the geometries up there. Now, even though you've only really looked at geometry of smaller molecules, and we've only done things that were really tiny, and that was a center, and then you looked at the things around it, you can actually determine the geometry of every giant molecule. You could just have to pick which specific things you're going to look at. You just focus on one center atom, and then you can determine the specific atom's geometry. And using that, you could, in theory, visualize the shape a molecule is going to take. Now, usually we'd use kits to actually visualize it. But you can figure out a kind of a loose idea of what the thing's going to look like. Now, this question here is because, again, last year I had kids who I didn't teach in chemistry. I know you guys know steric number because we talked about it in chemistry. So you just add together the number of atoms bonded to the atom in question plus any lone pairs. That'll give you steric number. I mentioned this a small amount, small amount in chemistry, but sterics in chemistry is referring to the facts that atoms occupy space. Even if they're tiny, they still take up space. So steric number is telling you how many pieces you have to give enough space to. If you go to college and you actually take organic chemistry there, you're going to talk about sterics a lot because sterics are a huge impact on reactions. One of the quotes that my professor in college for organics said, so much that it's burned into my brain, is that organic chemistry is mostly at the intersection between electronics and sterics, which is a whole lot of big words, but is basically saying you can learn a lot about organic chemistry by how it interacts with electricity and electrons, on how those positives and negatives interact, and the sterics, how much space things take up and how much room there is for reactions to actually occur. So we're going to do a geometry question here. We're going to actually look at what the geometry of all of the atoms in this structure are. And you might think that seems like a whole lot going on, but don't worry, it's not going to be that bad. There's a couple of things you need to remember. It's got lines without things clear on them. That means that this must be a skeletal structure, which means it's got to have carbons all around it. Remember, carbons have to have 4 bonds, so if it doesn't, we have to assume there's invisible hydrogens there. First thing we can do, all hydrogens, no matter where they are in this, all hydrogens have a geometry of linear because they can only ever bond to one thing, and the only thing that you can have connecting 2 dots together is a straight line. You can also go around and find all these things that are kind of poking out the sides. These oxygens here, this chlorine, those all, since they're only attached to one thing, even though there's 3 pairs of electrons around this chlorine, and there would have to be 2 pairs of electrons around this oxygen, we know that they're connected to only one thing, so it has to be linear. It has to be a straight line. Now, all we have to worry about is all of these carbons that are in here. So let's first look and try to find carbons that we know for a fact are going to be the same, or know for the fact are going to all kind of be in the same category. We can identify them together. So this carbon, for example, is connected to 1, 2, 3 things, but since there's a double bond, that still gets us to the magic number of 4 that carbon wants, so we don't need to add any hydrogens. Same with this one, same with this one, same with this one, and same with this one. So 1, 2, 3, 4. These 5 carbons are all connected to 3 things, 0 lone pairs. And if I flip back, 3 things, 0 lone pairs is a trigonal planar geometry. So we would call these guys right here would be trigonal planar. Now these guys right here only have 1, 2, 3, and 1, 2, 3, 1, 2, 3. These 3 carbons, the one right here, the one right here, and the one right here, only have 3 total bonds present. So that means there must be something else there. That means there must be a hydrogen attached to it. So that hydrogen is also kind of invisible, poking off here. We're just pretending it doesn't exist. It has, if you remember the meme, it has no place in this story. But that still means then that this carbon must be attached to 1, 2, 3, 4 bonds. 1, 2, 3 is the steric number with no electrons. So actually every carbon in this whole structure is trigonal planar. And all that leaves here is this nitrogen right here, this nitrogen that's attached to a hydrogen. Remember though, and this is one of the things that we hadn't gotten into yet, so I guess I shouldn't say remember, but you have to assume that there are electrons if they are needed to complete the octet. So that's why, for example, I said on this O, there's actually 2 pairs of electrons, because it needs to have 2 pairs of electrons to have 8 total electrons. The chlorine needed 3 pairs, so it had 8 total electrons. This nitrogen is attached to 1, 2, 3 things. That's 2, 4, 6 electrons. So it actually needs to have a lone pair here, which means it's bonded to 2 carbons, a hydrogen, and it has dots. So that's a steric number of 4, one of which is a lone pair. So that's going to be trigonal pyramidal, or a trigonal pyramid geometry. And I'm going to go and get the molecule kit really quick and sneeze. And I'm going to actually show you, with this awkward pause that's about to happen, that this is actually going to look like that geometry, and I'll prove to you that. my molecule kit. And you guys will be getting to work with these at some point, so don't worry if you're like, man, that seems like it's going to be the coolest part of this class. You're right, it's pretty cool. But so these black dots represent carbon. So I'm going to go ahead and start making my structure. So I need 1, 2, 3. This one's a double bond. You know, a good teacher probably would have had this stuff prepared ahead of time, but lucky for you guys, I've never promised to be a good teacher. Just get that there, that there, that there. This one's here. The white dots represent hydrogens. This blue dot represents nitrogen. I'm not going to add the oxygens of the chlorine, just because I don't want to sit here and have you be just staring at me making a structure for an absurdly long time. Now, if you remember from what we were just saying a second ago, the geometry of all of the carbons are trigonal planar, and trigonal planar is different from trigonal pyramidal in that they're all flat. They should all be completely flat and on even level with one another. And because of the way these molecule kits are designed, because they're actually supposed to be showing the actual geometry that occurs with each one of these, it takes a little bit of flexing to get them into place. Actually, I have enough that I can add. It's not didn't take me nearly as long as I thought it would. And we're going to add our oxygens. Hopefully on the right spot. Yep, on the right spot. Good, good, good. So they're all trigonal planar, except the stuff that's kind of on the outer edges, those were all linear, with the one exception of the nitrogen. And if I hold this up flat, some of it's angled a little weird just because of the way I'm holding it, but if I hold it up level, you'll notice that all of the carbons are flat because they're trigonal planar, and then these things were linear poking out the side. And you'll notice I was holding this one a little bit weird. That's because this was nitrogen. Nitrogen is the only thing that's popping out of the plane in this one, and that's because it has these 3 points. The electrons would be up here kind of bouncing around. So the fact that it's on these 3 points is what's making it a trigonal pyramid. It's trigonal pyramidal. So looking at every specific carbon, looking at this one, it's got a trigonal pyramid. This one, trigonal pyramid. This one, trigonal pyramid, etc., etc., etc. So you can identify the geometry of specific atoms, and like looking at this in particular, you can probably see. I'm going to hold this up a little bit closer because I just realized I forgot my camera is so small. But hopefully you guys can see that it is like completely flat. And if not, I'm going to make another video, and I'll show this in kind of a hand cam mode to make it a little bit easier. Let me know if you need me to do that. Again, this morning's not gone the way I intended it to. But we can just go back and use all of these geometries. And if you knew all of this stuff, and if you had all of these skills available to you, looking at this structure, you would be able to say, oh, this is going to be like completely flat, except for this little guy right here. This little guy is going to be poking out. And that is one of the beauties of being able to predict geometries. Now, there's going to be a couple of weird rules for this, but we'll talk about that a little bit later. I'm going to leave you with an intro to what we're going to talk about for our next set of notes, though, which is let's think about carbon. So we've got carbon. Got one of these little dots that represent carbon. Specifically, we're going to think of methane. So methane, I actually have always had one on my desk. I have it over here. So we've got methane. Methane is a carbon bonded to 4 hydrogens. Experiments and data have shown that all of the bond lengths are the same, the angle is identical, and that every bond is covalent, which makes sense because my structure, if I hold it up to the camera closer, I really hope I'm holding it close enough to the camera. It's not having 2 screens at school is getting really frustrating. But hopefully you can see that it's all even, it's all going all the way around, and all sorts of experiments have proven that that's the case. And we also notice the carbon will form 4 bonds. I want you to try to come up with a reason that the fact that carbon will do this, why might that be weird? And think about all the stuff we've talked about. Think of quantum numbers, think of electron configurations, think of geometries, think of all of that stuff, and try to come up, and you don't need all of those, I'm just trying to tell you all the stuff we've talked about. Try to come up with a reason as to why carbon doing this might seem weird, and then I'll tell you why it's not weird later on. So if you have any ideas, you can go ahead and make a guess. You can put it in the box of the as a comment on this video or something like that. Otherwise, I hope you have a great day. I hope you have a good week. I apologize this video was not as high quality as most of my other ones, but like I said, it's been a long morning. So I hope you have a great rest of your day. I hope to see or hear from you soon. See ya.